In section 2.5, we're going to look at transformations of functions. So in order to get this section started, one of the things that we have to recall and to be able to reproduce is those parent functions from section 2.4. So hopefully at this point, everybody kind of has that basic family of functions memorized. The first type of transformation we're going to look at is going to be the vertical shifts. Okay. Suppose I start with the graph of x squared. This is our basic parabola, it's a member of our parent family. We should know what it looks like. That's going to be the graph here in black. It has its vertex at 0, 0. Some of the key points that we're going to want to kind of keep in mind when we graph x squared, always keep track of the origin. Here it's by default at 0, 0. A couple other key points on the graph of x squared would be the point 1, 1, right? If you plug in 1, 1 squared gives us the output of 1. Same thing, negative 1, if you plug it in, negative 1 squared is positive 1. And if you plug in 2, 2 squared is 4. So you can see kind of like those points on the graph in black. Let's take a look at the function g of x now, which is going to be x squared plus 2. If we look at the form of g of x, it includes as a portion of it the parent function f of x, but with the addition of plus 2. So one of the ways that we can write g of x, we can relate it back to the original graph of f, which is our parent function. Its formula is nothing more than f of x plus 2. And its graph is the one showed here in blue. One of the things that we notice is that if you consider the points that are on the graph of g of x, their output value is going to be equal to the output value of f with 2 more added to it. The effect that that's going to have is that's going to be a vertical shift of the graph up 2 units. So to go from the graph of f of x to the graph of g of x, what we see is that every single point is simply going to get moved up 2 units. So the effect of adding 2 on the outside of a function creates a vertical shift. In this case, it's a vertical shift up by 2 units. If we look at the function h of x, which is x squared minus 3, again, looking at the formula for h of x, it again includes the parent function f. We could think of h of x as f of x minus 3. The heights of the function's h of x's graph at the value x is going to be 3 less than that for the graph of f. And if we look at the graph of h, it's the graph here that's in red. The way its graph is related to the parent function is that every point on the graph of f is simply going to be moved down 3 units to create the graph of h. So what is the kind of the overall pattern here? Adding on the outside of a function has the effect of moving the graph up, and subtracting on the outside of a function moves the graph down. Those are vertical shifts. Okay. To summarize, let's suppose we have the graph of a parent function. It's going to be depicted by the curves in black here at the bottom. If c is a positive number, and if you add a value to the function, the effect that it has is it's going to shift that parent graph up c units at every point. If conversely, if we subtract a number from the function f of x, the effect that it's going to have is it's going to vertically shift the graph downward by c units at every point. Let's take a look at example 1. We want to use the graph of f of x equals the absolute value of x to obtain the graph of g of x, which is going to be the absolute value of x minus 4. So starting off, we look at g of x, and what we take notice of is the thing that's going to catch your eye. The main part of g of x that's kind of the interesting portion is this absolute value of x, right? So that's kind of our parent function, and then what we're simply doing is we're taking that and subtracting 4 from it. We know that if we subtract, that's going to be a vertical shift. And in this case, because it's subtraction by 4, it's going to be down 4 units. So let's go ahead, let's begin by doing the graph for our parent function, f of x. At this point, we have to know what the absolute value function looks like. It's piecewise linear. It looks like a line with a slope of positive 1 for x greater than or equal to 0, and it looks like the portion of a line with a slope of negative 1 for x less than 0. Whenever we do our transformations, we also want to label some of the points on the graph. Some of the easiest points to kind of keep track of on absolute value, and one point you always have to give us is the vertex. Here that's at 0, 0. We also have a point at 1, 1. And then over here we have a point at negative 1, positive 1. All we are going to do to create the graph of our new function is we're going to take all of the points and we're going to shift them down 4 units. So to do that, let me just kind of shift down first those key points we were keeping track of. The point that was at 0, 0, if we move that down 4 units, 1, 2, 3, 4, that's going to have a new location of 0, negative 4. The point that was at 1, 1, we're going to move that down 4 units, 1, 2, 3, 4. That's now going to be located at 1, negative 3. And then over here to the left, the point that was at negative 1, 1 gets shifted down 4 units. And now it's going to be at negative 1, negative 3. Once you have a few points, we know what the basic shape looks like. We can then go ahead and graph this. And our answer to this problem, the function g of x, it's the graph in blue. And again, the way that we obtain that is we simply took each point for the graph of f, and we moved it down 4 units. Let's take a look at another one. Let's use the graph of the square root of x, which is our parent function graph, to graph g of x, which is going to be the square root of x plus 6. Okay, we identify, okay, the square root of x, that's our parent function. The fact that we're adding 6, that's going to be a vertical shift. And it's going to be up 6 units. So to begin, let's again begin by graphing the square root of x. Some of the key points on the parent graph of the square root of x to kind of keep track of would be these 3 points here. So this is what the parent graph looks like. Some key points are the starting point. This is the first x value, the smallest x value in the domain. It's at 0, 0. We have a point at 1, 1. And then we have a point at 4, 2, right? If you plug 4 into the function, the square root of 4 would give us the output of 2. So that's the ordered pair 4, 2. And now to get our solution, all we're going to do is vertically shift each one of those points up 6 units. So this point that was at 0, 0 now gets moved up 6 spots. That's going to occur at 0, 6. The point that was at 1, 1 is now going to occur at 1, 7. And then we had this point at 4, 2, which will now be located at 4, 8. Once we have a few points, we know what the overall shape looks like, we can go ahead and complete our graph. So this is the graph of g of x equals the square root of x plus 6. And we obtained it by doing 2 things. We know the graph of the parent function. We have those memorized from section 2.4. And in addition to that, we need to identify the type of transformation that's being done to that parent graph. In this case, adding 6 on the outside of the function has the effect of vertically shifting the graph up 6 units. So when it comes to the vertical shifts, these are ones that I typically find that most students kind of can latch on pretty easily. If you add, you go up. If you subtract, you go down. That kind of agrees with our intuition of like the positive values on the y-axis going up, negative values going down. The horizontal shift is something that I typically find that for students initially kind of might seem a little bit backwards, but let's explain what these are going to look like and what happens here. Okay, so let's go back to the graph of f of x equals to x squared. This is going to be our parent graph. And let's consider the graph of g of x, which is equal to x minus 3 squared. Okay. So the graph of g of x, we are subtracting 3. So the parent function, by the way, the overall thing that determines the shape of this graph is the fact that we have something being raised to the second power. So this is going to be a relative of the parent function x squared. But what we're doing, instead of just having x squared, we're subtracting 3, but that subtraction by 3 is taking place on the inside of the square. Okay? We can, again, relate g of x to the graph of f of x. G of x is simply found by taking f and evaluating it x minus 3. So the subtraction is now taking place on the inside of the function. Additions and subtractions that take place inside of a function are what's going to create horizontal shifts to the left or to the right. As it turns out, subtracting on the inside of the function is actually going to have the effect of moving the graph 3 units to the right. Okay. To consider why that's the case, let's just compare the graph of f of x and not the graph, but the function f of x and g of x. And let's suppose that I want to get the output value of 0. Okay. If I want to get an output of 0 for f, then pretty easily we can look at it and we say, oh, I know if I plug in 0 into this function, I get out 0. Okay. Now, what would be the similar value we would need to plug into g of x in order to get a 0 output? In other words, for what value of x here would g of x be equal to 0? Well, that we plug in 0 into f to get out 0, but notice that for the graph of g, because we're subtracting 3 on the inside, in order to get a 0 output, the value for x has to be equal to positive 3, okay? And that's the value for which g of x is equal to 0. In essence, one of the ways you can kind of think about it is to get the comparable value from g that we would out of f, because we're subtracting 3, we need to kind of overcome and compensate for that, which means we'd have to have an additional 3 on each x value to get the similar value out of g of x. So where we can just plug in 0 to get 0 out of f, we would need to plug in 3 into g to get the same output. Likewise, the value you would get if you plug negative 2 into the function f would be obtained by plugging in negative 2 plus 3 more, which would be 1 into the graph of g. So the effect is that each of these outputs are occurring at a value of x that is 3 more than the original for f, right? All of these x values are 3 more, and if you're increasing each x value by 3, the effect that has is that's going to take the graph and shift it 3 units to the right. Okay. So let's kind of summarize this with horizontal shifts. If you have a c value, let's say it's a positive number, so in essence, if you're adding on the inside of a function, that's going to shift the graph to the left c units. And if you subtract on the inside of a function by a value c that's positive, the effect that has, it's going to shift the graph to the right c units. Again, intuition, it might be a little bit counterintuitive perhaps, right? Usually we think of positive values on the x's going to the right, negatives going to the left. Yet here we are with function translations. If you add on the inside, that actually shifts the graph to the left. And if you subtract on the inside, that actually moves the graph to the right. Let's take a look at example 3. We want to use the graph of f of x equals x squared to obtain the graph of g of x equals x plus 5 squared. So we look at the graph of g, or look at the expression for g, and we see that at its heart, it looks like something that's to the second power. So that immediately makes us think that this is going to be a relative of the parent function f of x equals to x squared. We can rewrite g of x as f evaluated at x plus 5. So the transformation here is we have an addition on the inside of the function, right? We're adding 5 on the inside of that square, and that's going to be a horizontal shift. adding on the inside actually shifts it to the left. So it's going to be a horizontal shift left by 5 units. Once we've identified that, we now begin by graphing the parent function. So let's again graph the function x squared, kind of highlighting some of those key points. We said the vertex at 0, 0, 1, comma 1, negative 1, 1, and let's do a couple more. 2, 4 is always good, and negative 2, 4 is good. And that gives us our basic parabola shape. So these are going to be points on the graph of f of x. Let me just maybe make a mini table here. Negative 2, 4, negative 1, 1, 0, 0, 1, 1, and then 2, comma 4. Because this is going to be a shift, this is going to be a shift, we said, to the right, to the left 5 units, every point here gets shifted 5 to the left. So this point, which is at negative 2, 4, is now going to occur at 1, 2, 3, 4, 5 to the left. It now takes place at negative 7, comma 4. The point at negative 1, 1 gets shifted to the left 5 steps. 1, 2, 3, 4, 5. It's now going to occur at negative 6, comma 1. The origin, which was at 0, 0, gets moved over to negative 5, 0. The point at 1, comma 1 is now going to occur at negative 4, comma 1. And the point at 2, comma 4 gets moved over now to negative 3, comma 4. Once we have our few points, we can go ahead and draw the graph. Again, how do we obtain this? Well, we simply took every point on the graph of f and we just moved everything over 5 units. So it was 5 units to the left. Let's take a look at another one. Here we want to obtain the graph of g of x equals the square root of x minus 3 via transformations. This is simply going to be the square root function, but we're subtracting 3 on the inside. Subtracting 3 on the inside of a function is going to be a horizontal shift. And that's going to be 3 units to the right. So let's start with the graph of the square root of x. Our parent function, square root, has these key points. We have the point at 0, comma 0, 1, comma 1, and also 4, comma 2. You can kind of go ahead there and draw the overall shape. The next thing we're going to do is we're going to take each of those points and we're going to shift them 3 units to the right. So this point that was at 0, 0 is now going to occur at 3, comma 0. The point at 1, comma 1 now appears at 4, comma 1. And the point at 4, comma 2 is now going to appear at 7, comma 2. Go ahead, complete the graph. And then this gives us our graph. So this is the graph of the square root of x minus 3. It's the square root function, but simply taking each point and shifting it 3 units to the right. The next thing we can discuss is combinations of vertical and horizontal shifts. So oftentimes the graphs we look at don't just have like one transformation or another. Oftentimes they have multiple transformations. For instance, if we look at the graph of g of x equals x minus 1 squared plus 3, at the heart of what's going on with this graph is we do have something to a second power. We realize that and we say, okay, that's going to be a relative of our parent function f of x equals x squared. From there, to kind of figure out what's going on with it, we have two things that are occurring. We have a subtraction by 1 on the inside, and we have an addition by 3 on the outside. The subtraction by 1 on the inside, we recognize that that's a horizontal shift. That's going to be to the right 1 unit. And then we also have this addition by 3. That's going to be a vertical shift up 3 units. So not only do we have to move each point 1 unit to the right, but in addition, we have to move the points up 3 spots. To do this, we can begin, let's draw the parent function first, as always. So we're going to begin by doing the graph of x squared, which looks like this. So here's the graph of x squared. And now we're simply going to take each point and we're going to move it both up 3 and to the right 1. So I'm going to move this point right here over 1, 2, 3, up 1. This point gets moved over 1, 2, 3, up 1. The point that was at 0, 0 gets moved over 1, 2, 3, and then up 1. At 1, 1, we move that over 1, 2, 3, and then up 1. And then lastly, the point that was at 2, 4, that gets moved over 1, 2, 3, and then up 1. Once you have your points all moved over, then just simply go ahead and connect the dots and make the pattern. We know the graph of x squared is a parabola, and so this is what we have. This represents the graph of g of x equals x minus 1 plus 3. And actually, I might have shifted these too far. What did we do? 1 second here. So I went over 3 and up 1. I was supposed to go over 1 and up 3. So my apologies, that's not even right. So quick restart here. Let's actually get the correct graph on here for everybody. Even online videos contain mistakes. So we're trying to make this an authentic class experience. I'm prone to at least a couple mistakes in class. You get one here on the video as well. No big deal, quick fix. My apologies. So here's our graph of x squared, and we're moving over 1 and up 3. So over 1 and up 3 for each point. Over 1, up 3. Over 1, up 3. Be right here. Over 1, up 3. Over 1, up 3. And then lastly, over 1, up 3. That's better. So now this truly is the graph of g of x. We took each point in the graph of f, we moved it over 1. So each point on this graph got moved over 1 and then up 3 steps. Let's do another one. We want to use the graph of the square root of x in order to graph the square root of x plus 4 minus 2. When we look at g, obviously kind of in terms of form, the thing that's going to catch our eye is the fact that it has a square root in it, which lets us know that the parent function is going to be f of x equals the square root of x. From there, we do have a couple of things that are being done to that graph in terms of transformations. We have the addition by 4, which is taking place under the square root. So that's inside of the function. That's going to be a horizontal shift. Remember, horizontally, if it's adding 4, that's 4 to the left. So we're going to shift this 4 units to the left. And now we have a subtraction by 2 on the outside. That's going to be a vertical shift. And that will be down 2 units. So first things first, let's start off with our parent function. The square root of x, again, a couple key points you always want to kind of keep track of here. 0, 0, 1, 1, and 4, 2. It's going to look like this. To each point, we need to both move it to the left 4 and down 2. So over 4, down 2. The point was at 1, 1. We move it over 1, 2, 3, 4, down 2. So that should be there. 1, 1. That was the point that was at 1, 1. Got moved over 1, 2, 3, 4, down 2. And the point that was at 4, 2, we move that over 1, 2, 3, 4, down 2. It's going to end up right there. Now that we've done this, we can go ahead and connect our dots. And we know what the overall shape should look like. So this is the graph of the square root of x plus 4 minus 2. It's the graph of the square root function, but with each point simply moved over 4 to the left and then down 2. So 4 left and in addition down 2. The next effect that we're going to look at with the graphs is either multiplying by either the inside or the outside by a negative value. In particular, here we're trying to look at a negative coefficient of 1. Okay. If you multiply a function on the outside, so if y is equal to negative f of x, the way that this new graph will be related to the parent graph of f of x is that it's going to be a reflection with respect to the x-axis. In essence, what you're doing is taking every y value from the original graph and you're changing its sign to the negative of f of x. The effect that that has is, for example, if I look at the point that was at 2, 4, if you reflect that by changing the value of the sign for the y coordinate, the point that we would now get would be 2, negative 4, which is simply reflected across the x-axis. So multiplying on the outside of the function by a negative, that creates a x-axis reflection. Let's take a look at example 7. Use the graph of f of x equals the cube root of x to obtain the graph of the negative cube root of x. Let's go ahead and do this one. For the cube root of x, this isn't one we've done too frequently yet. Some of the key points on the cube root graph are these. So my parent function, we have 0, 0. The cube root of 1 is 1. And then the next value to get an exact value out of would be the cube root of 8. The cube root of 8 is actually equal to 2. So that produces the order pair 8, 2. Similarly, one of the things that's nice about odd roots is we can have the odd roots of negative numbers. The cube root of negative 1 is negative 1. And similarly, the cube root of negative 8 would actually be down at negative 2. Again, this is a shape cube root function that hopefully we all have memorized at this point, or will shortly. So this is the graph of the cube root of x. In order to graph the negative of the cube root of x, we look at it and say, okay, we have a multiplication on the outside by a negative. That's going to be a reflection. A lot of times you'll see me use this abbreviation. It's very common. WRT means with respect to. So with respect to the x-axis. All that means is we're going to take every single point and reflect it across the x-axis. If a point is on the x-axis, then it doesn't get reflected at all. It's actually a fixed point. This point here is going to get reflected down to here. This point's going to get reflected down to there. This point gets reflected up, and this point also gets reflected up. If we go ahead and connect the dots, maintaining the overall shape, we can see how that transformation works. We now have a point at -8, 2, at -1, 1, 0, 0 is still there. We have a point at 1, -1, and a point at 8, -2. So by multiplying on the outside by a negative, we obtain the graph of the negative cube root of x. It's simply the reflection of the parent graph across the x-axis. The next kind of reflection we're going to look at is what happens if we multiply on the inside of a function now by a negative. If we think about a point, for example, let's suppose we start with the original graph, the parent graph, y equals to f of x. So this is going to be a point that's on the graph of the original function. If we substitute in and plug a negative into the function, right, or multiply the inside by a negative, then what's going to happen is that point that was located at this positive x value is now going to be located at the negative of it. So to make a long story short, when you multiply on the inside of a function by a negative to the variable, the effect that it has is it's going to be a reflection, but it's the reflection about the y-axis. So this piece here gets reflected across to here. This piece here gets reflected across to here. In terms of ordered pairs, like for example, if I call this the ordered pair for argument's sake, say that it's 2, 4, you're going to have the ordered pair -2, 4 on the graph of y equals to f of negative x. So it's kind of simply taking each of the x values and moving it over to its negative. And that reflects across the y-axis. Let's take a look at example 8. We want to use the graph of the square root of x to graph the negative x square root. We look at the graph of g. Obviously, we see the radical, so we know that the parent function is going to be the square root of x. Having that multiplication by a -1 on the inside, that's what's going to create the reflection with respect to the y-axis. To begin, let's go ahead and draw our parent function's graph. We know that the square root graph looks like this. There we go. And now all we're going to do is we're going to reflect it across the y-axis. This point is on the axis of reflection, so it's a fixed point. It doesn't move. The point at 1, +1 is now going to get moved to -1, +1. And the point we had at 4, 2 is now going to get moved to -4, 2. Like this. So this is the graph of the square root of negative x. It's simply a reflection with respect to the y-axis of its parent graph, which was the square root of x.